Okay, so this week we're going to return to this question of fine-tuning, and I think one of the earlier cosmological arguments around fine-tuning, and this was to do with the initial expansion rate of the universe. So the universe, born in the Big Bang, it's expanding at a certain rate, and that rate is governed by the stuff in the universe.
Yep.
And there are several possible outcomes. There's one, of course, where the universe expands at a nice rate such that matter can collapse and eventually form galaxies. But there were other potential outcomes. The universe could have been expanding far too fast, and that would mean that matter rapidly sort of dilutes in the universe, and so you don't have a chance to form galaxies. Or the universe could actually recollapse. The pull of gravity pulls on the expansion. The universe recollapses in a time much shorter than the time it takes for a galaxy to form. So people have said, well, if we go back early enough, when we take a look at the earliest expansion of the universe, it appears to be fine-tuned to a very high degree to allow us to be here today. What's it telling us?
Well, this is a really interesting case because, like you said, so we start today, we see the universe around us, we try to infer what's happened in the past, and if we look at, if we want that nice sort of expansion today, we haven't recollapsed yet, structure's still forming, and we take that target and we go back into the early universe and see how big the target is. It depends how far you push it back. But there's a time when we have a very good idea that the Big Bang Theory is working nicely. That's called nucleosynthesis. It makes predictions about how much helium there is in the universe. Those predictions are roughly right, and so we're in pretty good ground there. That's 1 second. If we go back to that time, then you've got a target which is 1 part in 10 to the power of 16. And if you push it back even further to where it's called the Planck time, and we would need basically as far as we'd want to push Einstein's theory of gravity, because we don't have quantum mechanics involved. If you push it back there, you get something like 1 part in 10 to the power of 60. You've got to make sure that the relationship between the expansion rate of the universe and how much stuff is in the universe, you've got to get that right to that level in order to make the universe sort of work out nicely later on. Now, that sounds like a really great case of fine-tuning, except that there's a lot more to be said about it, because one of the things that could have tipped people off early on was when you look at the target that they've got to hit, already inside that target, here's the life-permitting bit that we've got to hit. Inside there is a special condition already waiting for us called flatness.
Aha.
So the universe as a whole can have a certain geometry.
Yes.
Okay. So within Einstein's theory, it can have a flat geometry. So if you draw a great big triangle in the universe, all of the sides add up to, and do the angles on a side, they add up to 180 degrees. But there's other geometries possible. If you drew a great big triangle in a positively curved or sort of spherical universe, the angles in a triangle would be more than 180 degrees. And you can also have negatively curved universes where it's less than 180 degrees. And these are real proper physical properties.
So what you're suggesting is that life-bearing universes are ones which appear to be flatter because they have the right kind of expansion to allow structure to come together. If you've got geometries which are highly curved one way or the other, then it's either eventual recollapse or a rapid expansion, and that sort of is not good for life in the universe.
Yeah, that's basically it. So flatness is that line between, if you're positively curved in the early universe, unless a cosmological constant saves the day, let's ignore that for the moment. If you've just got matter, and in the early universe it's only matter that matters anyway, if that's a sentence. Positively curved like a ball, it's going to recollapse. Negatively curved, if you're very, very negatively curved, if that's a way of saying it, then structure stops forming very early on, so you probably won't get that. Now, the fact that there's already some special condition waiting in there says, okay, there's a way we could solve this problem without worrying about what life needs. We just need some process or some reason or something that aims for that target. And if we hit that target, we'll get life thrown in for free.
Yeah.
And so starting in the, probably late 70s, but the early 80s, really, it was realized a way that the universe could aim for that target. And what you need is a period in the very early universe, very, very early universe, super early universe, where the expansion of the universe is accelerating. So it's getting bigger, and it's getting bigger faster and faster.
I think we need to rewind slightly, though, right?
Okay.
I mean, I think, so we're talking about the work by Alan Guth,
Yep.
and this thing called inflation, as it came to be known. Now, his motivation, though, wasn't to look for how to hit a target to find life. He was dealing with another problem which might sound kind of weird, and that's this notion of magnetic monopoles or magnetic charges. And when we look at electromagnetism, we see that Maxwell's equations are quite symmetric, right, in terms of electric fields and magnetic fields, but not exactly so. And the things that are missing is that for a magnetic field, you create those with currents, and electric fields, you create those with charges. But you could equally write out Maxwell's equations to have electric fields created by magnetic currents, and magnetic fields created by magnetic charges.
Good.
So
you've done that beautifully.
I know. Just trying to get that all right in my head there. So you could perfectly symmetrize Maxwell's equations, and physicists love beautiful equations.
We do,
but don't mention that to Sabine Ossenfelder. But so if you assume that the universe at some level was perfect and beautiful and symmetric at the start, we would expect there to be electric charges and magnetic charges in the universe, because we'd have symmetric Maxwell's equations. But of course we don't see any magnetic charges around us today.
What happens if you try and chop a magnet in half?
You mean today?
Today. Why can't I get a North Pole? I just I get a magnet, I chop off the North Pole now.
Because in our universe, they always come with just north and souths together. So you chop up a magnet, you just get a smaller magnet, and you never end up with just a North Pole or just a South Pole.
Okay.
So how do you get around that? Well, one way you could do that is assume that there's a particle that's associated with a magnetic charge, and you can create those in the universe. And the way that it works is that you can only create particles in the universe if the temperature of the universe is higher than the mass of that particle. Right?
This is E equals mc squared.
E equals mc squared.
You got to pay for it.
Yes. So if you've got a very hot universe, you can create massive particles, but as the universe cools down, you can't make them anymore, and then you can only make lighter and lighter particles, and you get all the way down to electrons at the end. So Guth's idea was that maybe the universe was very hot at the start, bubbling along, creating these magnetic monopoles, right? Now, at some point, the universe gets too cool to make any new monopoles, and you have freeze out. You can't make any new ones, but they're still there. Right? So they still bounce around doing their things, but we don't see them today. So he said, well, I wonder if I could come up with a mechanism that would take the universe as it was at these very early stages and dilute everything. So rapidly dilute everything such that there's one magnetic monopole per observable universe, and then just carry on the rest of the Big Bang as normal. So then you start creating all the other particles, and eventually get electrons. And then you say, well, then Maxwell's equations themselves are in fact truly symmetric, truly beautiful. It's just that there's only one magnetic monopole inside the universe. But you got something else for free, right? So you rapidly expand the universe in the early universe, inflation.
And then suddenly, if that happened, that target, instead of it being a really small target that the universe tends to move away from, during that inflationary time, magnetic monopoles being thrown far and wide, you head towards that condition of flatness. So you can sort of think of this if you had a sort of wrinkly balloon and then you blow it up and it looks smoother and smoother as you go. That's not a bad analogy for what's going on. And there's a couple of other problems that it seems to solve, but we'll focus on that fine-tuning one. The question now is, how do we make the universe do that thing?
Yes.
How do we make it happen? And in particular, there's some criteria we need. So as you said before, the expansion of the universe is governed by the stuff in the universe. So we need a new type of thing in the universe which makes its expansion accelerate. And it can't be the same it can't just be a cosmological constant. It can't be the sort of thing that's doing it today, because this is way too slow, the sort of accelerating expansion we see today. So we need that form of energy. There needs to be some time when inflation starts. So at some point, it's not enough to just have this form of energy hanging around. It's got to be the dominant form somehow. It's got to switch on. It takes over the universe and causes the expansion to accelerate. It's got to continue for long enough. In particular, the universe, in order to flatten things out just right and probably solve the monopole problem and these other ones as well, the standard number is the universe has got to double in size about 80 times. So 2 to the power of 80. Now, if you've got exponential expansion, that's probably not such a problem, but it's got to continue. It's then got to stop, because our universe isn't inflating, and if the universe doesn't stop inflating, life definitely won't happen, because you're emptying out the universe. You're doing the thing that the empty universe was going to do for the fine-tuning problem anyway. And fifthly, okay, you've emptied out the universe. There's almost nothing there except for this inflation energy. Once you've stopped, you've got to get that energy and you've got to dump it back into the stuff of the universe. And in particular, you want to create just the low energy stuff. Don't make monopoles again, or you've just...
What's the point?
What was the point?
Yeah.
Okay. So the idea is we made monopoles when things were really hot, and then inflation happens, and then when we reheated the universe, as it's calling, we put all the stuff back in. We put it in a lower energy form. Didn't make monopoles. And finally, if you want to explain our universe, it better not be the case that the universe ends up totally perfectly smooth, because our universe isn't totally perfectly smooth. We know it started off with a level of lumpiness, which is small. It's 1 part in 100,000. So if you grab a bit of the early universe and you measure the density here, and you grab a bit over here, roughly, those numbers will agree to 5 decimal places and not agree after them. So that's the crucial number, 5 decimal places. So 1 part in 100,000.
But just to clarify that, so you don't want it to be significantly less smooth, but you also don't want it to be significantly lumpier, right?
Yes.
Because then things collapse very rapidly and matter gets processed into black holes very fast, and so you don't get stars and etc. So you want this Q value, as you said, about 1 part in a 10 to 100,000. Is that kind of ballpark? So
this is an interesting question of what life could put up with. Actually, Fred Adams has got some interesting papers on this. If you start making Q larger, make the universe lumpier, the first thing that happens is all your galaxies end up much denser. Yeah. And the problem with that's going to be, okay, here we are in our solar system. We've got a star. We've got planets going around. We just need the rest of the universe to leave us alone. All right. If another star comes wandering through, that's a bad outcome. So if you have universes where you make all your stars, but all your stars are totally in binary orbits, and they're all, no planetary system's going to form because it'll just get unbound by a star wandering past 10,000 years later or something. But one of the things that Fred's been looking at was, what if we could survive sort of in the outer reaches of galaxies? Like, there'll be no life in the middle. There's probably not life in the middle in our universe anyway, in the middles of galaxies.
Yeah.
So that's an interesting open question, but there's definitely a limit there. Certainly, you start overdensities in the universe start to collapse very early on, and in particular when there's still radiation pressure. The pressure of the photons still matters, and that makes a very different sort of catastrophic collapse into a black hole, possibly. So we started off with a fine-tuning problem of how we're going to hit this target, and then we got this idea of inflation. We've got an idea about a process which is going to take us from wherever we are, from a universe which is maybe not hitting the target, and it's going to send us towards the target. But now that's not the end of the problem. That's the main sort of take-home message here. You don't then just go, hey, we're done. So you now have to ask, is this thing fine-tuned?
Yeah, let me just think about this. So when Guth wrote down the mathematics, right, there were some numbers he had to put in there to control inflation, right? Like, how strong is this field, which is called the inflaton field, how strong this field is, and how rapidly it changes, and all these kind of things. So you have to put numbers into inflation, and different numbers give you different kinds of inflation. So you could have inflation that starts and stops very quickly, or inflation that happens really slowly, or etc. So what happens?
So one of the crucial things in most modern models, there's the crucial thing that you specify when you say, here's my model of inflation, is something called the potential. So you can sort of imagine here's the sort of the field that's wobbling. And the question is, okay, I've got this much energy in the field. If I just left it there, what would happen next? Would I get less field or more field? Electric field, something like that. And so a way of thinking about that is, okay, you could draw some sort of shape and think about a ball rolling on that shape. And so if it's tilted this way and the ball is here, then I tend to go to that value of the field. And if it's tilted the other way, I would tend to go that way. So the shape of this potential tells you which way the field tends to go, and in particular how fast it gets there. And what we discovered with inflation was, to make these work, there has to be some bit of that shape which is really flat. So we wherever you come from, your inflaton gets onto this plane just really slowly, and this is why when inflation is happening, and then inflation's got to stop, right, for all those reasons before. So there has to be some other shape on the end there.
So it has to have a very particular kind of shape. So it sounds already like it has to be tuned, right?
You can't just throw any old thing on there and expect inflation to happen.
Okay.
Even then, that's a sort of an interesting problem. There's an interesting paper by Max Tegmark from sort of 10, 15 years ago, just called I've forgotten the name of it now.
But you put a link in.
We'll put it in the link, and I'll might dub over
and
my
then,
voice here.
Then write an email to Max to apologise for forgetting the title of his paper.
Something like, how probable is inflation, or what do we have to do to get inflation? Where he just said, all right, let's just make a random shape, this huge landscape of things, and then just throw down starting points all over the place and see what happens. And so, yeah, like you said, so in particular, the last point I said there, you've got to get this Q value out.
Yeah.
If you just have a single potential, you have to tune the shape of that potential to get the right value of Q out at the end. And now, it's not quite as fine-tuned as the 1 part in 10 to the 60, but it's still fairly fine-tuned. And so this is actually called the fine-tuning problem of inflation. And so we've got some issues there. We've got to think hard about, all right, we had some sort of idea about, what was possible in the early universe and what might happen. And now we've got to think about what sort of inflation things could happen.
Okay. So where do we stand then? I mean, inflation seems to have solved some problems, but itself has to be fine-tuned to get the solutions that we want. So is it really a satisfying solution?
Well, it's kind of hard to tell. This is one of the things we actually talk about in our new book, Cosmic Revolutionaries Handbook. So we use inflation as an example of something where let's just watch cosmologists have a debate at the moment. So if you want to get in on that debate, if you want to challenge the Big Bang Theory, here's an example. So there's this sort of back and forward that inflation has some very high-profile opponents within the cosmological community. One of the guys, Paul Steinhardt, who was initially... You've mentioned Alan Guth. There's actually sort of a group of people there who were all roughly in the right area at the right time, thinking about the right things. Starobinsky and Linda and Steinhardt's one of them, and he's now, all the hope of this thing being a lovely predictive theory, as he's abandoned it. He doesn't think it is going to be a predictive theory, and so. Where we're at the moment is we're sort of waiting. We've got toy models, like you draw the right shape, and some of the right things seem to happen to set up our universe, and they really do look good. Like, it's amazing that this flatness problem and initial conditions and a few other things like horizon problem, you can solve it if you just get a nice burst of acceleration at the beginning of the universe. That's an interesting result. We're just sort of twiddling our thumbs waiting for someone to come up with a really nice and natural and inevitable sort of inflation potential, or to finally put this thing to rest and give it a reason against it. We're sort of in limbo. Most cosmologists, I think, are in inflation's corner. Yeah. But we've still got some fine-tuning issues there to think through. Yeah.
Now, before we finish, you just used a word there, which I think our listeners might have pricked up their ears a little bit too. And it's a word we hear a lot when we talk about various theories, the word natural.
Natural.
Oh, natural. Yeah. Now, do you want to spend a minute on natural, or...
Well, natural's something you say about your own theories, and you're very skeptical when someone else says them about them. So let's give an example of a time of a theory where everyone went, yeah, that's the best. So general relativity. So Einstein, one of the reasons Einstein's theory is so famous is because it's so nice. So he starts thinking of some simple thought experiments, and one of the crucial ones is if you're falling in an elevator and you can't see the outside world, right? You're in a bit of trouble. Hopefully, nice things happen as you get to the bottom. But as far as you can tell, in your little elevator, if you start doing experiments, it would be identical a scenario to if someone had just switched off gravity. And that's kind of interesting because gravity we think of as a force, and falling in an elevator, I mean, gravity's definitely there. You're just moving in a certain way. And Einstein thinks really hard about those things, and he has his great insight that maybe gravity is just the curvature of space-time, and you put all of those ideas into some interesting mathematical formalism, and then out comes Einstein's general theory of relativity. And there's sort of one free parameter, but we know how gravity works in the solar system. We have it's basically Newton's free parameter. We know what it needs to be. We've measured it, and so we'll give him that one. And the rest of the theory is just kind of there. And it almost... not that it couldn't be otherwise, but any other way you could start with where Einstein started and try to get to a theory of gravity, you have to make it more complicated to where Einstein got. And in that sense, natural's such a loaded word. I mean, we're trying to describe nature. The whole thing's natural, right? There's something so nice and satisfying about that we didn't have to make some ad hoc assumption along the way. We didn't have to throw in some weird parameter. We didn't have to we didn't have a million options. We just picked one at random.
Yeah. And lots of explanatory power. That's the other thing, right?
We apply it. It can account for everything that Newton's theory can account for, and then it can account for the fact that Mercury doesn't quite go around the way Newton said it would, and light is bent past the sun in a way that Newton's theory didn't quite explain, and a whole host of other things.
Yeah. So
natural is something that we know what that sort of feels like, but it's really hard to pin down.
Yes. It's like the famous definition of pornography. It's hard to define, but I know it when I see it. I know
when I see it.
Yeah.
So with inflation, there's sort of a natural bit in the middle of where accelerating expansion solves a whole lot of stuff. But then when we try to build a theory that explains where this accelerating expansion comes from, none of those look really natural. And so we're a bit stuck at the moment, and we need some help. So come and do a PhD.